Hello everyone. Here we will discuss the encoding with linear code. We have seen in the last class how two codes are equivalent. What do you mean by that equivalence of linear codes? Now we'll have the article on encoding with linear code. This will be lecture number 18. Let capital C be an NKT linear code over FQ. Let capital C be an NKT linear code over FQ. What it means? It has length n, dimension k, and distance d, and it is a vector space over the field fq. Here each code word of C can represent each code word of C can represent one piece of information. And you know this, what is the size of C? Size of C is q to the power k. So C can represent, because dimension is k, so C can represent total q to the power k distinct pieces of information. Distinct pieces of information. Each word can be treated like this, distinct pieces of informations. And here, since dimension is given, so once basis is known, once a basis R1, R2, since dimension is k, there must be k linearly independent vectors in C which spans V. So once basis R1, R2 is fixed in C, once this basis is fixed in C, each code word V, or equivalently each of, there are total q raised to k, each of q to the power k pieces of informations, q to the power k pieces of information can be uniquely written as a linear combination. As you know, every vector in V can be written as linear combination of vectors from basis. Can be written as a linear combination. Can be written as linear combination as follows. How one can written? So V is one code word, one representative. We can find the scalars u1, u2, and uk, since dimension is k, basis are k, such that V can be written like this, where this u1, u2, u3, uk are scalars from field. Scalar means from field. What equivalently we can say? Equivalently, we may set matrix G, whose each row will be the first basis, second basis, and kth basis, to be a generator matrix. To be a generator matrix for this code C, whose ith row will be Ri. in this above chosen basis. The order is fixed here. That is given vector, that is given vector u, u1, u2, uk. It is k tuple. So definitely it is from fk. The field is fq. So what is clear to you that so now it is clear that it is clear that v can be easily written as, okay, v is given u1, r1 is first basis, u2, r2 second basis, and so on, uk, rk kth basis. So it means you consider this matrix of order 1 rows and n columns. It will u1 is multiplied to the first row r1, u2 is multiplied to second row r2, and uk is multiplied to the last row rk. And this matrix is your, the first matrix is u and second matrix is g. So in this way v is written as ug. V is written as ug. And this v is a code word from C. Now conversely, any v in C can be uniquely written. Can be uniquely written. Any v in C can be uniquely written as v equal to ug, where one can find this easily u1, u2, and uk. And this is a part of vector. This u vector is from f to k. Since it is k tuple, dimension is k, that's why. So what it means, every word, not from C, I'm saying every word u from fqk, every word from fqk can be encoded as, this can be encoded as v. This can be encoded as v, and this v is given by u into g. So this u is encoded as v. Meaning of this is, and the process of representing u of fqn is as a code word v equal to ug in C is called as encoding process. Okay, I'm writing this. The process of representing, the process of representing the elements, the process of representing elements you are from fqk. The process of representing elements of this u as a code words v equal to u into g. This is done in C is called, this process is called encoding process. This is called encoding process. Okay, let us, we'll see by the example here how one can encode. So let C be having 5 length and dimension 3, linear code over binary feed f2, and I'm writing the matrix as 1 0 1 1 0 0 1 0 1 1, and the last row 0 0 1 0 1. Writing this matrix as generator matrix means the row vectors of this G forms basis for C. Let G is generator matrix, generator matrix. Then encode the message. Then encode, since dimension is 3, so whatever you are taking, this U must be from F to 3. So you take any element from up to 3. I will take this element 101. Encode. There are total 8 elements in this up to 3. We can encode all those matrix. The encode 101 from up to 3 using generator matrix G. Using generator matrix G. So encoding process, it is just like this. U V equal to U into G. And we want to encode this U as a V. Encoding done in C. Yeah? So you need to find this V. So what is U? It is 101. What is G? Okay, it is given. And easily one can find this product. 10. This is the row is multiplied to first column. It gives 1. Row multiplied to second column gives 0. Row multiplied to third rows, it is 1 plus 0 plus 1. 2 means 0. Row multiplied to third column, 1 plus 0 plus 0, so it is 1. And row multiplied to the last column, it is 1 into 0, 0 into 1. We are multiplying this column, 1 into 0, 0 into 1, and 1 into 1. So 1, 0, 0, 1, 1. So this U can be encoded as V, like this. So this is your V. Encoding of U in C is V. We can also note from this example. Note that the information rate of C is. How one can find information rate? Information rate can be found by using dimension divided by length. That is 3 bits out of 5 are used to carry message. 3 bits out of 5 are used to carry the given message. To carry the given message. Okay. Another note or remark. One should make another remark about this. What are the advantages when G is standard matrix? Advantages of G as a standard matrix. Write down the advantages of G. When G is standard matrix, what advantages you must have? So these two remarks are the advantage. When we can have many more advantages also. Some of the advantages having generator matrix of linear code in standard form will be described as follows. So first, if G is in standard form generator matrix, suppose dimension of that code is K, the standard form will like this. If G is directly standard form, then easily one can find its parity check matrix H by using the algorithm. And what is that? Minus X transpose I n minus K. If its length is n, the K n minus K will be the parity check digits for that. So this is most important advantage of generator matrix if it is standard matrix. If you know the standard form of the generator matrix, the parity check matrix easily computed by using the algorithm. Directly you can write this. And what is second algorithm in encode? Second advantage, it's in encoding process. If an NKD linear code C, NKD linear code C has a generator matrix G in standard form. So I'll not mention dimension of C, its dimension is K actually. In standard form IX, then automatically the parity check will be this minus X transpose I n minus K, since dimension of C is here K. Okay, we don't need parity check while in encoding. Then what will be u into g? U into g can be easily done. U multiplied by I x. So this is the row multiplied to this matrix. So u into I and u into x. It will looks like this. U into I is u and u into x is ux since I is identity matrix. So first k digits are the code word of u. Here you can look at this first k digits because its length is k and here length is n minus k. The k bits related to here and n minus k bit related to by looking at this order. Huh? This order is k, obviously k by n. Among n column, first k columns will be here and n minus k columns will be there. The first k digits in the code word v equal to ug gives the message u directly. Here, if it is standard form, the first k digit will be your message u directly. You don't need to compute directly. You can write the first k digit in the code word v equal to ug is the message u, and they are called message bit. They are called message bit, and the remaining n minus k digits are called check digits. One can call it as parity check also. This remaining n minus k digits are called check digits. So message bit plus check digits is always n. The number of message bit plus check digits is always n. So n minus k related to parity check matrix. So in some books it may referred as parity check digits also. The check digits represents this parity check bits represent redundancy in the added message. This can be represented as redundancy in the added message. Why redundancy is added? To protect the message against the noise. The redundancy is added in certain messages, so you can call it as redundancy bit also. So let us have some example for process of encoding and all. Let us have some example on that. It is from exercise example 4.32 of your textbook, page number 71. So question is assign messages to the words in F23 as follows. This is given statement. No? The question is next year. Okay, I'll write F23 is all element. 0, 0, 0, F23 there are very total 8 elements. 1, 0, 0, 0, 1, 0, 0, 0, 1, then 1, 1, 0, 1, 0, 1, 0, 1, 1, and the last digit is triple 1. So for this word, you can call it as A. A is assigned to this. C is assigned to this. D is assigned to this. E is assigned to this. G is assigned to this. I is assigned to this. N is assigned to this, and last O is assigned to this. So total 8 words. A B C D, not A B C D, A C D E G I N O. These 8 words are assigned. Now let capital C, the linear code always represent capital notation. Let capital C be the binary linear code with generator matrix, binary linear code with generator matrix G equal to, and the last row is this. So this is 3 by 5, its length is 5. This is generator matrix, obviously which is not in standard form, but no need to put in standard form. Use this G to encode the message. Use this G to encode encode the message, encoding. So for each, now you just find encoding of is this word, encoding of A, encoding of C, encoding of D, encoding of E, with the help of the generator matrix, and we have explained how one can find the encoding of this. So C is 5 length and 3 dimension. We can find distance also, but we need to know what is parity check for this, and for the generator we can compute parity check matrix also. Let's see with the binary linear code, binary, okay, or up to you can see. And each message having length 3, each message have length 3, so you have to write all the element f to 3 element, you have to write all the f to 3 elements. So all f to 3 elements are this. Okay, these are the 8 objects. Now this is your first vector, second vector. Okay, these are represented by some letter notations. Okay, we'll apply for, or we can do, okay, 000 A C D E like this. It is encoded. It is coded as A C D E. For 101, it is I. For 101, it is I. For 011, it is N. Okay, I changed this order. That's why for 01, it is N. For 110, it is G. And for last, it is remaining O. Just keep in mind these words for it. So encoding of this, encoding of A in C. This is the C linear code. It is your first word. Okay, I will call it as V1. V1 equal to AG. What is A? And write generator matrix. Okay, 0 into something will be 0 always. Okay, I will write generator matrix 1 0 1 0 1 0 1 0 1 0, and the last row. Okay. See, because of the zero matrix, now it will be, this matrix is of order 1 rows and 3 columns, and this is 3 rows and 5 columns. Product has to be 1 rows and 5 columns. So you get this 0 to first column, 0 to second column, 0 to third column, 0 to fourth column, and just matrix multiplication you get. So your V1 is, V1 AG is this. Next V2 equal to CG. What is C? It is 1 0 0, and G is there 1 0 1 0 1 0 1 0 1 0 0 0 0 1 1. Okay, second two digits are 0, so 1 into 1, 0 into 0, 0 into 0, so it is 1 1 0 1 0 1. Like this product you can get, you can check easily. So V2 is CG, it get as 1 0 1 0 1. This is V2. You need to find all 8. Now two we have done. What is next? D. Next is D element. So I call it as V3, D into G, D 0 1 0, and write matrix G. Okay, this multiplication, the first row multiply to 0 and second row multiplied to 0, and addition is done. So first row, first column will get 0. First row, second column will get 1. First row, third column will get 0. First row, fourth column will get 1. First row, fifth column will get 0. So V3 is, D is encoded in C as V3, and it is 1 0 1 0 1 0. Next, V4. V4, I write it as next element is E into G. What is E? E is 0 0 1. So write E, and the G matrix is 1 0 1 0 1 0 1 0 1 0 0 0 0 1 1. So this product we need to perform. First two elements are 0. So you get 0 0 0 1 1 like this. You can check this. So V4 E is encoded as V4, and it is this. Now remaining four elements are there. Remaining four elements are there. So next is V5. After D, I'll write E, E into G, and E is given as, okay, what I have written here. The 001 is E actually. The 001 is E. Okay. So after E, G should be there. I should use pen for it writing. So this G is a code word, and this G is generator matrix. Keep in mind. What is a code word? 110 is a code word. This is generator matrix. You should represent G by another notation. Okay. In the question itself was not mentioned. Okay, no, not to worry. Just keep in mind at this case, this is from the for the message this 110, and this is the generator matrix that you should keep in mind. So 10101 01010 00011. This is generator matrix G. And now the product. The last element is 0. Okay, we are only multiplying to first two elements in each column. So 1 into 1, 0 into 1, 0 into 0. 1 into 0, 1 into 1, 0 into 0. 1 into 1, 0 into 1, 0 into 0. So multiply to this column. So 0 into 1, 1 into 1, so it is 1. And at last 1 into 1, 0 into 1. So it is all 1. Okay, this V5 is G is from this G is generator matrix. I call it as GN, and it gives like this. This is actually V5. This is actually V5. So three calculations are remaining now: V6, V7, and V8. So V6 will be after G. The letter is I into G. What is I? I stands for 101, and G is the generator matrix 10101 01010 00011, and do this product. So 1 into 1, 0 into 0, 1 into 0. So 1 into 0, 0 into 1, it is 0, it is 1, it is 1, 1 into 0, 0 into 1, 1 into 1. And at last 101 multiplied to 101, it gives 2, 2 means 0. So finally V6 is IG, you get 10110. Next V7, small V7, you have to write N into G. After I, N is there. So N is represented for 011 and write generator matrix 1 0 1 0 1 0 1 0 1 0 0 0 0 1 1 and do this product 0 into 0. Okay, this 0 is multiplied to each, it becomes 0. Only thing is that 0 into 1, 0 into 1, it is 0. 1 into 1, 0, 1 plus 1, 0, and 1. Okay, let me correct if something is wrong there. 0 1 0 0 1. Calculations, you can check calculations, all calculations. The procedure is important instead of calculations. So v, small v, it is not vector. You are writing small v for encoding of O, encoding of O with respect to generator matrix G. Who is this O? O is 111. And G I am writing once again same generator matrix. So 0 1 0 1 0 0 0 0 1 1. So this multiplication is 1, this is 1, this is 1, this is 1, and this is 0. This V8, all the V's are unique, keep in mind this, no repetition. So V8 you get at O into G equal to like this. So you have find for all. You have find for all. So you want to encode this encoding. Finally, encoding can be written like this. Now you have to be careful while writing. For E, what I have written for E. Okay, where is E? For E, it is 00011. For E, it is 00011. What is for N? For N, it is 01001. 01001. For C, C will be the earlier part. Okay, we'll see there. For C, it is 10101. 10101. 10101. For O, O will be the last. This is for O. You are writing in place of this. Now for D, it is the third V3. It is V3 actually. For D, it is V3. It is 01010. 01010. You are writing 5 bits. This is for E, N, C, O, D. Now next will be I. Continuously you should write I. I is encoded as, where is I? Okay, we find for I. Okay, I is encoded as 10110. 10110. The next two words are remaining, N and G. What is N? We have written here. N is 01001. This is for N. And G should go back through find this. G into G and we have written, okay, all one. G is all one. So V1, V2 are V8, but only write in order encoding. So this is the encoding of the message encoding. The message encoding is done here. Now what will happen? You have some communication channel. You're passing your messages. Whatever messages, raw messages, you have to code it like this. You have to encode the message in your query feed. Suppose some X message was sent to this noisy channel, and then Y is received. Here you are encode it, and you are sending this whatever message you have sent. Suppose the same encoding was x, this x was encoding, and some other message is coming like this. Uh, any message you are coming like this, you have to properly detect what message was sent by using some encode decoding methods. So proper detection of proper x, finding that same x was sent, that process is called decoding. That we'll see in the later class. Till then you can try for the example of generator matrix in standard form, exercise 4.33, exercise 4.34, and we'll see more example in the next lecture. Okay, thank you. Thanks for watching the video. Thank you one and all.